Okay, kiddos, this is the last video I can make in the classroom today. I'll have to provide after this, I'll have to provide you maybe something from WebEx. Maybe I'll provide videos utilizing maybe a TV or a whiteboard, maybe trying to make sense of some other documents that way. But this is the last classroom video I'm able to make in the last 3 days. It's been a long haul. So we're gonna finish it up talking about our solar system. This is our star and the planets that revolve around our star. We'll focus on what those things are, what the names of those planets are, how we classify them, and then we're going to look at the reference tables to see the data that's associated with each of these planets. All right, so solar system. It's a star, could be a group, a binary star system, if it's not our star system, that then have satellites that revolve around them. Satellites that revolve around a star could be planet, could be a comet, could be asteroid. Now, we also have other objects that revolve around planets. We call them moons, right? Or purely just satellites of a planet. Now, in our solar system, we have 8 planets. I would love to debate you on Pluto, but not for now. Our solar system is believed to be 4.6 billion years old. So we are taking the assumption that the sun and the planets all began forming 4.6 billion years ago. And that was due to using uranium half-lives to determine that. All right, so the parts of the solar system. Most of the solar system, most of the mass and matter and material are in the sun. Okay? Planets, asteroids, comets, as I said, are satellites, and moons are satellites of us. Now, there are 2 categories of planets. You have our rocky planets. They're made of rocky composition. We call them terrestrial planets. So starting from the sun, which is not a planet, we have Mercury, Venus, Earth, Mars. Those are the 4 terrestrial planets. All of them have densities that are high due to their rocky composition. Okay? They have a surface that can be landed on. Okay? Jovian planets are the remaining ones. We call them gas giants. So after Mars, you have an asteroid belt, then you have Jupiter, Saturn, Neptune, Uranus. That's in order. Now these are mostly composed of gas. Some of them have solid and metallic hydrogen cores. Only recently science has been proving with empirical evidence that metallic solid hydrogen does exist. That gives some clout to the core of our gas giants being maybe solid. All right. Now, to give you some pause for scale, here is a scale image of the sun. This is not in the order of the planets by their assignment, their sequence away from the sun, but rather the size. So we have our sun, Jupiter, Saturn, I think that one was Neptune, Uranus, Earth, Venus, Mars, and then Mercury. So Earth, that little dot on there, that little dot, compared to the sun. Again, giving us more pause for understanding the scale and how humble we really ought to be about this planet, considering how small we are compared to the planet. All right? Asteroids. Let's get into talk about asteroids. Many of them are irregular in shape. They tend to be solid, rocky, metal bodies. There's been a lot of, hype in the news, a little bit of fear in the news, maybe kind of the fringe news, talk about asteroid impacts and, close calls with asteroids. Just read your news, make sure it's legitimate, okay? So the asteroid belt tends to be where these are found. They tend to bump each other in and out of their orbit of the asteroid belt, which is why we do get asteroids that pass us and end up in an orbit in a different elliptical orbit around the sun. All right, comets. Comets are composed of solids. Normally it's a solid gas or it's maybe solid water vapor, so that when these things are flying around the sun tends to heat them up and that heating process causes the tail of a comet to form, because that's the gas that's escaping, or that's the water that's escaping and turning into a gas to create that tail. Now a tail, like most of us would think, it follows behind us when we're running or going somewhere. So something's tailing behind you. It's not quite the same idea for a comet. So as a comet is orbiting the sun, it ends up solidifying way, way out in its orbit. And then as it comes in, it starts to melt or sublimate, turning from solid to gas as it gets closer to the sun. But the solar wind blows that gas away from the comet. So the tail is actually pointing directly away from where the sun is. So when you're watching a comet or you see a comet in the sky and you see the tail, that tail is actually pointing directly away from the sun. So if you were to follow a straight line and continue through the comet, it would lead to the direction where the sun is. So these tails, again, point away from the sun. All right. Another celestial body that we're going to talk about are meteoroids. These are objects that pass through our atmosphere, burn up, and sometimes if they make it to the ground, they land, they become meteorites. Okay? Sometimes there's large explosions. Most of the time we don't even know they're burning up as they come in. We are starting to see a little bit more depending on the dash cam footage that people are giving us from their cars. So we do see more, but chances are we're just identifying them more rather than them happening more. So just keep that in mind. All right. Before we get to our guided independent practice, I do want to go here to the reference tables on page 15 so I can introduce to you the solar system data chart. So please make sure you're open to page 15. So here we have our celestial object. They are in order from closest to the sun to furthest from the sun, and you should enhance the borderline between where it says Neptune and Earth's moon. This information is separate. So, celestial objects speaks for itself. Mean distance from the sun in million kilometers away. The sun is the sun, so there's no distance from it itself. And then we can continue to see that here we have Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune. The distance is increasing in millions of kilometers. Notice where it says 4,498.3 million kilometers. They wrote it a lot like we learned it in geologic history's time scale topic. So it's like saying 4.4 billion kilometers. Okay? Now, period of revolution. You have to start remembering the difference between revolution and a rotation. Revolution. Around the sun. Rotation. Spinning. Okay? Don't say spinning though. We've got to be prepared to use the vocabulary for these celestial objects. So, rotation of a planet, and then revolution of a planet. Let's get back to talking about this column. So, revolution, we've got days and years. So, we've got a D for days, a Y for years in this column. Notice that as you get further away from the sun, the revolution increases. So it gets longer and longer and longer in terms of Earth time. These are Earth days and Earth years that it takes for these planets to go around the sun once. Neptune, 164.8 years. Saturn went around it 29.5 years. Oh, that means Saturn's been around the sun once since I've been alive. It's on its way or going around the second time. My grandmother just witnessed Uranus going around the sun once, revolving around the sun once. Okay? Also notice Earth, 365.26 days. Notice we are a little bit longer. Okay, so if we get too far ahead of ourselves, we've got to make adjustments for that. Okay, rotational period of time. So how long does it take for these planets to rotate once in Earth? Hours or days? Notice Takes the sun 27 days to rotate once. Takes Mercury 59 days. It takes Venus 243 days. Okay, so one thing to point out here with Venus, the amount of time it takes Venus to rotate once is longer than it takes the whole planet itself to go around the sun once. Earth Day, we're short. 3 minutes, 56 seconds every day from 24 hours. That's why we add a leap day to the calendar. Okay? Now, Mars is very similar to us. Jupiter, the bigger the planet, the faster it rotates. 10 hours. So Jupiter rotates roughly 2.5 times, a little more than 2.5 times in one Earth day. So Jupiter's doing a lot of movement for that big planet. Okay. Now, eccentricity, we will discuss this column in more detail once we get to motions of the planets, but this deals with the shape of the orbit. Equatorial diameter, so the diameter across the equator of these planets, you have your distances in kilometers. Remember, if you're doing anything with circumference, this is diameter, so you have to turn it into a radius before you did pi r squared for either area or pi d for circumference. You've got mass, so this is how many Earth masses these things are worth. 333,000 Earths worth of masses in the sun. Outstanding. Earth obviously gets a 1 because it is itself. And then you see that there are fractions, if not multiples, of Earth here. You do have densities for these objects. If you notice, there is one which everybody likes to highlight, Saturn. Technically, if there was a bathtub big enough, which I don't know why you'd make a bathtub big in the first place, but if you did and you filled it up with water and you put Saturn in it, it would float like a rubber ducky. All right, so I've explained this a bit to you. Get familiar with it. Maybe pause before we go into a guided. If not, stay with me, and we're going to go to these questions here. So you've got question 1 and question 2. I know, I don't like wasting paper either, but the way this program prints it out, this question was too big to put with 1, and it doesn't rearrange all of them to fit nicely. So if you could, for now, answer question 1 and question 2, and then we'll go over it. So pause up, try it out. Okay, we're back. Just in case you didn't pause, yep, we took our mini pause. All right, so Jupiter is a Jovian planet. Compared to terrestrial planets, Jupiter has A. Well, we've got to figure out which one of these things makes the most sense from our data on the reference tables. So make sure you've got your, there we go, reference tables. Told you, unapologetically unedited, except for like 2 videos I had to clip a couple things. But otherwise, unapologetically unedited. So let's go back to the reference tables. Does it say Jovian planet anywhere? Does it say terrestrial planet anywhere? No, so you know what? Let's add that in before we answer this question. So here, let's create another borderline. Okay. Let's extend this out so that the Earth's moon doesn't get caught up in this stuff. And let's label this area here. This is going to be the terrestrial. I'm going to run out of room. Woo! Again, unapologetic. There we go. Good enough. Terrestrial. We're going to try to make this one smaller. Jovian. There, got that one in. So our Jovian planets are gas giants, our terrestrial. Let's get the sun is not a terrestrial planet, so let's get another line in there just to make sure that you don't get confused. All right, now we gotta figure out what that question was again, because you know what? It's good to go back and forth just to check. So, terrestrial planets. So compared to terrestrial planets, Jupiter has A. So let's see. We've got Jupiter here. Jupiter looks like it has a greater distance. It looks like it has a longer revolution. Longer revolution, looks like it has a shorter day, looks like it has a bigger diameter, and it looks like it's less dense. All right, let's see which ones of those work. So it's shorter period of revolution, no. It has a longer one. Shorter distance, no. Greater density, no. Let's go back and check mass. Yeah, it has definitely a greater mass. So we are choice 4. All right, this one, if you didn't, you need to take a moment to read through this. It's going to take us a moment together to be able to read this one too, so we can solve it. Figure 1, base your answer to this question on the passage diagram below and on the data table, and on your infinite knowledge of Earth science. The diagram compares the inner planets of our solar system to the planetary system surrounding the star Kepler-62, which is located in our galaxy. So the data table below shows data for the planets in Kepler-62 system. Kepler-62 system. Got planets, 62 with letters, all right? Kepler-62 planetary system, let's read a little more. 5 planets orbit a 7 billion-year-old star, much older than ours. Kepler-62, which has a surface temperature of approximately 4,900 Kelvin. 2 of these planets are located within the habitable zone. Habitable zone. Think about us, habitable. Is our planet habitable? Yeah, our planet's habitable. So maybe it has something to do with that. Which is the region around a star where life may exist due to the possible presence of water in liquid phase. The shaded areas in this orbital diagrams below indicate the habitable zone of each system. So here we have this shading for habitable zone. This shading, or the absence of any shading, is the non-habitable zone. So that's for Kepler-62. Now for our solar system, this is the habitable zone. It shows our planets in which ones are habitable. And here it shows which ones are in the habitable zone. So we've got, in this case, it looks like 62E, 62F are in the habitable zone. 62B, C, and D, nope, they're in the non-habitable zone. Okay? Down here, looks like Venus is barely in the habitable zone. Earth and Mars look like they're in the habitable zone. All right, so we've got planets and orbits. They are drawn to scale. So all these are drawn to scale. Very important. That means we can actually compare the sizes of everything here. Data table. Name of the planet. We got 62B, C, D, E, F. Then we've got distance from that star in millions of kilometers, increasing further away. The equatorial diameter compared to Earth's diameter. So these are a factor. This is saying that this is 1.31 times the size of Earth. Okay? Now let's see what we've got. This particular question may or may not deal with all the information, but clearly if there's this much information, there might be a couple questions associated with it. It says, refer to figure 1 and answer the following question. Identify the names of 2 planets in Kepler-62's planetary system that may have liquid water on their surfaces, and explain why these planets may have liquid water on their surfaces. Well, we'd have to come back here and understand what that means. So liquid phase of water, we've got to find something in the habitable zone. Okay. So we've got 62E and 62F are in the habitable zone. Let's just make sure that's what's it says. Identify the names of 2 planets in the Kepler-62 planetary system that may have liquid. So right here, we've got at least our 2. 62E, 62F. That's our, no, it's not our answer yet. Well, that's because it asks why. So we know at least what 2 are here, and the idea is explaining why the habitable zone is so nice. The habitable zone, it's warm enough to have liquid H2O. the whole reason why we have liquid water. We're in a zone where it's warm enough, but not too warm and not too cold, that we can have that liquid water on our surface. Well, kiddos, it's been real. You've got some more questions for independent practice. You've got your access points. You've got your notes. You've got me. If you want to leave some comments below on the video or any of the videos you've seen, I'll keep trying to answer those. I'll meet you up in WebEx for our tutorials and so on. But the last 3 topics of the year will probably be a different format. We got plenty of time, at least from the point I'm standing at right now, to start planning for that. Then we're going to do review, and if the Regents is still going, we'll get prepared with reviewing that so that we can do a lab practical and you can be successful on the written test. Besides that, it's been really awesome and tiring at the same time, but I am absolutely thrilled to have been able to provide to you 20 videos in these 3 days so that you can stay on track this year and not skip a beat with me. All right, hang in there, everyone. If we're not in a place where this is passed yet, I hope we are by the point we're watching this when we need to. All right, bye.